The ratio test is useful for series involving factorials or exponentials. The series a sub n converges if the limit of the absolute value of the next term divided by the term before is less than 1. The sum diverges if that ratio is greater than 1, or if that ratio is infinity. The ratio test is inconclusive if the limit of that ratio is equal to 1. So if the ratio test yields 1, you'll have to use another test to determine convergence or divergence. So how does the ratio test work? Consider the following sequences. A sub k is a geometric sequence, but b sub k, not quite. While the formula for the sequence b sub k is very close to that of the sequence a sub k, it is not a geometric sequence. With that said, let's take a look at the ratio between each pair of terms. That ratio would be the next term of b divided by the term before. It's not going to have a common ratio because it's not fully geometric, but it does look similar to that, so let's take a look at some of those ratios. If you divide the second term by the first term, you get 0.57. The third term divided by the second term is 0.58. Notice how these ratios are not the same. They're not a common ratio, but the limit of their ratios does seem to be approaching 0.6667, or 2/3. If the limit of the ratio of the terms is approaching a number, and that number is less than 1, like it would have to be if it were a geometric series, then your original series will converge by the ratio test. Even though this is the lesson on the ratio test, could you think of another test to tell the convergence or the divergence of this series? What about that nth term test? If we take the limit of this expression as n approaches infinity, we actually do know that n factorial grows at a much faster rate than 3 to the n, so this limit will equal infinity. Oh my goodness, that means this series diverges by the nth term test. If this were a practice problem, you would stop right there and be done with the problem. But I still want to show you how to do this with the ratio test. This would be a sub n, so a sub n plus 1 replaces every n with an n plus 1. Remember, the ratio test does the next term divided by the original term. So we'll take that a sub n plus 1 divided by a sub n, or multiplied by the reciprocal of a sub n. The most common error that people make when working with the ratio test is confusing it with the limit comparison test. For the limit comparison test, you take the original series and divide by your comparison series. But for the ratio test, you take the n plus first term and then divide by a sub n. Some things I'm going to do in order to reduce is to expand the n plus 1 factorial to be n plus 1 times n. And I could keep going, n minus 1, n minus 2, but I can stop there and put a factorial because I know that it will reduce with the n factorial in the denominator. I'm also multiplying by 3 to the n in the numerator. In the denominator, I can separate 3 to the n plus 1 as 3 to the n times 3 to the 1. This is also being multiplied by n factorial. Let's reduce. Our absolute value is really just there if we have an alternating series. N is approaching positive infinity, so we no longer need the absolute value. We could even take 1/3 out of our limit. And when you plug in infinity, you get 1/3 times infinity plus 1. That's definitely infinity, so this diverges by the ratio test. We were only using the ratio test to confirm what we already knew from the nth term test. Don't waste your time with more difficult tests if you can determine the divergence of a series very quickly with nth term test. For number 2, first of all, I see that if it were just this, I could actually rearrange to make it a geometric series, and then I could determine its convergence or divergence based on the geometric series test, but I have this pesky n squared in the denominator, so just a lot of exponents and things going on, meaning ratio test is an excellent candidate in order to determine convergence or divergence. This will be our a sub n. To get a sub n plus 1, we're going to replace each n with an n plus 1. Let's simplify. Now plug it in to the limit to complete the ratio test. Let's expand anything that we may need to or that may help us to reduce. We can begin reducing. Again, the absolute value is really just to eliminate the alternator in an alternating series. So because n is approaching positive infinity, we can take away the absolute value. We really only need to consider terms of highest degree in the numerator and the denominator. So 3n squared over 4n squared. This reduces to 3 over 4. All right, 3 over 4, is that greater than or less than 1? That is less than 1. Therefore, our series will converge based on the ratio test, which you can write as RT. Now you may notice that number 3 is an alternating series, so you could use the alternating series test for this one. In order to use the alternating series test, we need the limit of the non-alternating part to go to 0. And we need to know that each consecutive term is less than or equal to the term before. Sometimes if you can't immediately see if this is a true statement, just start plugging in some numbers. Remember, our very first value of n is 2, so I'm going to plug in 2, and then I'm also going to plug in a larger number. That is a true statement. Maybe I'll plug in 99. This is also a true statement. So this series converges by alternating series test. But since we're learning the ratio test, what would happen if we tried the ratio test on this series? Negative 1 to the power of anything is 1 or negative 1, but since this is absolute value, those are not going to affect our numbers at all. So if we took the terms of highest degree, we would have n to the 1/2 times n over n times n to the 1/2. Oh my goodness. This gives us a result of 1. And when your ratio test gives you a result of 1, the ratio test is inconclusive, which is why using the alternating series test was a better idea and probably more efficient because you have more experience with it. Whoa, what's going on in number 4? We've got a double factorial. What does that even mean? That means every time you expand, instead of subtracting 1, you're subtracting 2. So this was 2n plus 1, now 2n minus 1. Now 2n minus 3. Notice how the difference between those is not a negative 1, it's negative 2. Let's find a sub n plus 1. All right, let's evaluate the limit using the ratio test. We're going to expand anything that might be helpful in reducing. This 2n plus 3 double factorial, we can expand. Remember, you're subtracting 2 this time, so 2n plus 3 minus 2 would be 2n plus 1. We could keep going, but we already have a 2n plus 1 double factorial on the bottom, so we'll stop here so we can reduce. N plus 1 factorial can expand to be n plus 1 times n, then n minus 1 times n minus 2, and so on. But we could leave it there with just a factorial. Let's reduce. Let's distribute. That would be 3n plus 3. And we don't need those absolute values because we know n is approaching positive infinity. And 2 over 3 is less than 1. So this series, the original series, converges by ratio test.